Swayam Prabha. Digital India. Educated India.
Okay, so I'll just give a brief idea about this ruled surface. So this ruled surface, basically what it tells is that, so if you, of course, I hope that you people know about normal. So at a point on a surface, you draw a normal. Okay, we are going, and then you take a plane containing that. And if you rotate this plane about that, and if one in any one direction, if the entire plane coincides with coincides with the object on a line. Okay, this is a line. So then this surface is called as a ruled surface. Okay, so it is kind of a conceptual definition on that. So if in the previous case of bilinear, what can you say about it? Is that a ruled surface? So the bilinear surface is a ruled surface or not?
Sir, but why are we rotating this surface? I didn't get it exactly.
No, we are not rotating the surface. You are only rotating the plane. And if the plane coincides with the surface, underlying surface in a straight line. Like
Okay,
for example, if you take a get one curve like this, or some other curve like this, or maybe another curve like this, correct? So that won't be a straight line. So if you take the case of a cylinder that we saw previously, okay, so we can see that this is also a cylinder actually, maybe not a full cylinder, half cylinder. So if you take a plane, that is passing through the normal, and then you rotate that plane, you can see this plane, one of these edges will coincide with one of the edges here.
okay.
I mean, conceptually, right? Not a surface. This won't be a surface intersection like what you have on my left hand here. So it won't end up in some curve like that. It will end up in a straight line here. Did you get that?
Sir, so this end of the plane needs to be perpendicular to the original surface in that case.
Along the normal, yeah, along the normal. That's what he said, coinciding along the normal at that point. Correct. In a sense, it is perpendicular to start with, but we say this plane is coinciding with the normal. So when you do that, you can find if you can find at least one straight line in the model, then that means it is called a ruled surface. I mean, it's only conceptual.
Can you please repeat this once again? Due to some network issues, we couldn't follow it.
Oh, I see. Okay. So what I'm trying to say is that if you have a surface like this guy that you have here, and if you have a normal at any point on the surface, maybe I'll go back and come. So just a minute. So are you guys seeing this slide now?
Yes.
Okay, so the idea of a ruled surface is that, so I take a point on a surface, and then I take the normal, okay? And then I take a plane that coincides with the normal, so to speak. And then if I rotate that plane along the normal, something like this, and in case if it finds a straight line on the model, in one direction at least, okay, then this surface is called as a ruled surface. For example, when I take a surface like this, generic surface, and I take a normal, let's say, and I take a plane, okay, and if I rotate it, so it may be in some other position like this, let's say, but it may generate only a curve, not a straight line as what you see here. That will coincide with, let us say, this one of the thing. In a sense, I mean, it's conceptual definition, not that it has to coincide, it generates a straight line. That is the idea. This entire straight line is lying on the surface, whereas here it will be something like a curve. So this is not a ruled surface, whereas this is called a ruled surface. Is that conceptually okay?
Yes, I got it.
Now you go back to that hyperbolic paraboloid. Is that a ruled surface?
So please show that picture again.
That's a bilinear surface. So is this surface ruled or not?
Yes, sir. Because it looks like we can make normals in two directions.
So this surface is not, this surface is actually called as a doubly ruled surface because you can find two directions in which that happens. You're exactly right. So this is actually a doubly ruled surface. So a hyperbolic paraboloid is a bilinear surface and hence it is also a doubly ruled surface. Whereas here you have it is a singly ruled surface. So in the other parametric direction, whatever you do, you'll always get a circular arc, right? Let's say if it's a cylinder, you will get a circular arc. That's not going to be straight line. So this is a singly ruled surface. It's very useful and it is being used in lot of designs. I think particularly in aerospace applications and if you use all the softwares like CATIA, which are all tuned to use these models, I think I hear that a lot of applications, particularly in aerospace, make use of these ruled surfaces idea. Okay, so that is about, there are singly ruled and doubly ruled. That is what we discussed. Okay, so only one question is that this one, find out what is a developable surface. Okay, as an exercise. This is what is a developable surface. It's kind of very closely related to the ruled one, but I would say that you try to work out what is a developable surface. Okay, now we come to our precious one on the Bezier and the B-spline. Okay, you have to take a deep breath and do you guys understand this picture? Any clue, any answer?
So I think we are trying to generate a surface using Bezier curves.
Any other idea? Any other thinking? Other guys?
Three-dimensional convex, three-dimensional convex something within which our surface will be Bezier
Okay.
surface will be.
I'll give you one hint. I'll give you one hint. I mean, it's of course difficult. So, what is the input for a Bezier curve?
Sir, the points, the points of the convex hull. The
Array, come on. How many times I have told that terminology?
Control points.
Control?
Points.
Control points. Okay. Essentially, that will form what? That will form a
convex hull,
Convex
sir.
hull.
yeah. Oh yeah. Control points will form what?
Control polygon.
Control
Control polygon. That is what I want. Okay, I have a set of control points, and then if I join them, you may or may not close it. This is called as control polygon. Okay. Now see if there is, if this picture is somewhat related to that in terms of course, surface. So what can you say about it?
So control polygon, just that we are having points outside the two-dimensional surface.
No, but even your 2D polygon also can be a three-dimensional space curve. That also you can do. We didn't, as I told you, right? We didn't talk about space curves there in Bezier, but you can have same three coordinates for each of V0, V1, V2, V3, X0, Y0, Z0. That also could be a three-dimensional one. So what is it?
Are we trying to take the tensor product of two Bezier curves?
Yeah, in a sense, tensor product, it's a tensor product. But what is this figure indicating to you? In terms of control polygon itself, what is that in 3D you can think of? This also I used in the morning. Okay.
From 3D
What?
area
Polygon
into
surface.
Yeah, but I didn't use the word surface. What is that I used? Because surface we are using for, revolution, rule surface, Bezier surface. What is the term that I told you in the morning? Guys completely forgot that. So you remember I used the word control net. I showed the word control net or control polyhedron. Do you guys remember or
Yes,
no?
yes. You use the word net somewhere.
Yeah.
Yes, okay.
So in 3D, it is a control net. What is the control net? Or it basically it's a control polyhedron, also we can say. So how this control polyhedron will look like? And this actually looks like what you have here, except that it is very difficult to understand. That is a, it's a control net is what is that been shown, or control polyhedron is what it has been shown. But unfortunately, it is also shown with boundary curves, so kind of difficult to figure out. Okay, let me just quickly try to give you some understanding of how this picture looks. I have to move these guys here. Okay, so how this picture looks, you know that in the case of Bezier, what is the notation we used? B?
0 to B1.
Okay, B0, B1, B2, B3. You remember that, right? And then we know that it is in one direction. So the curve is in, let's say, U direction. Okay. Now remember we have U. So we have U direction and then we have W direction or V direction, whatever. Okay. So you have U direction, you have W direction. So now how this guy will become? Okay. The notations also will get changed accordingly. Okay. And remember that this degree is associated with the number of control points. Yes or no? Degree of the Bezier curve is determined by the number of control points, isn't it? That's what we saw in the morning.
Yes, sir.
Correct. Now remember you have one direction in U and one direction in W. That means I can have 1 degree of curve in this U direction. I can have another degree in the other direction. So confusing, huh? I think all have become silent. Okay, so let me try to draw better on that. So what happens here is that I will go to a fresh slide, maybe. Okay, this is, okay. So let me go here. Go even. So suppose say I show this picture here, which is as nothing. So let us say that you want to have a curve of degree 3 in U direction. What is the number of points that you require?
4.
You require 4
4.
points, correct? Suppose I want a degree 2 in the W direction. What is the number of points that you have to do?
3.
Okay, so the total control point, or in terms of control net, it will actually be 4 into 3. So you need 12 control points, which is called as a control net, so that you can actually get a Bezier surface, which is 4 by 3. That means you can have degree 3 in one direction and degree 2 in the other direction. Okay, how does that work? So I'll just start with this 4 guy. Remember, you have 2 directions. Okay, remember this is U and this is W, so to speak. Okay, now I am starting with this 4 guy, which you all understand hopefully now. This is the U direction. So now we know that there are 2 indices coming in, because on the other direction also I have to have another index. So we start notating this as B00, B10, B20 and B3. Okay. Now you talked about 3 points on the W direction or in this direction. Okay, let me go to another one. Remember the starting point is still the same. And then I could have a net, let's say I have 3 points. Remember this goes in the W direction. Okay. So this point is now B00 and then this is B. What should be this notation?
0, 1.
B01, then
0, 2.
B02. And now this is all over the place. So I am going to have a similar 3 curves from here, which is B10, B1, sorry, B0.
B1, 1.
So this is B11 and then B12. Correct? And then another guy, something like this. and then this is B. What will be the one?
B21, B22.
Okay, B21, B22, and then one more like this. This will be B31 and now this guy will all get fully closed in the sense, okay, you have to connect these guys also, and then these guys also. So how many control points you have now? How many control points you have total?
12.
12.
4 by 3, you have 12 control points for the entire surface that is forming a control net. Guys, are you able to make out what is happening?
Yes, sir.
Little bit?
Yes.
So this is how you have a control net for a Bezier surface, and then you can generate the Bezier surface using the similar set of equations that we saw in the morning. Okay, all other properties will remain very similar on that. Okay, except that what will happen here is that you will have a boundary curve, one curve. What will be the notation for this boundary curve? Which control polygons will use the boundary curve? This will use the B00, B10, B20, and B30. Okay, this will be one control, one curve, one of the boundary curves. And then you will have another boundary curve. What will be the control points for this boundary curve?
B00, B01, and B02.
T02. And then you will have one more curve for this. And then let's say one more curve on this. So these four boundary curves will form this entire surface path. This is also a four-sided path. So any other point is likely to involve all the control points that are available in this control net. Okay. So then how do you visualize better? Okay, so obviously this three-dimensional picture, you can actually try to draw for 5 by 4 or, whatever be the number, it doesn't matter. So to make it little bit easier, okay, we are going to use the following picture. Okay, so this is not exactly a planar figure, but just for a notation, you can see this is U direction and this is W direction, and we see the indices of the control points. It is like flattening your entire control net onto a plane. Okay, so it is not a planar control points. It's only a representation of the control points. You basically flatten this guy. You are able to understand this better now. This is what it is, a 4 by 3 or 5 by 3, or what is this control net here?
4 by 4.
Okay, this is a 4 by 4 control net. So what is the degree of curves on either direction? It will be
3.
okay, it will be cubic on either direction. So this is a bicubic Bezier curve that you will generate. So you can also look at, if you can recall, what was the algorithms that we saw in Bezier? Any idea?
So difficult names for
So recursive,
D
recursive
Casto
linear
and one other.
interpolation.
What is the name of the algorithm? Tell me one
D
of the.
Casto something.
Okay, one was decaslu. Next one was using what Bernstein basis. We saw that another algorithm. Correct.
Bernstein, yes.
Yeah, it's a Bernstein basis. So if you remember decaslu algorithm, what was that thing? Is a success linear interpolation done in a successive manner. So you take any u value or a t value and then take other points and then you do this. Then you keep doing something of similarly you do this and you get another. So this final point is on the Bezier curve. Correct, isn't it?
Yes, sir.
Give me some feedback. So how
Yes.
do you do this here? So you take a UW pair on each of these square boxes, okay, or near square in terms of not exact square, I have a rectangular subset of these control points. Okay, if you go back to this picture, okay, you can see that, okay, it is like you take this entire set onto one patch there, correct? That is what we are showing in this particular site, isn't it? So what you should do, how do you apply this decast here?
Do we extend the two-dimensional algorithm to one-dimensional to two-dimension by just considering a square instead of the line?
Correct. So how do you do that now?
You will need two parameters instead of one for T, I think.
Instead of one, correct? So we will use U and W. Once you use U and W, let's say you have some UW and get to this point, correct? And then what you can do, similarly, you can do in all the other guys. Remember, it is going to lie somewhere, but it looks like it is lying on the plane, but this is more of a representative. Now you will get another net, like a new control polygon that you had in 2D. You are going to have a new control net in 3D, like this. Isn't it? Now you do the same thing. You do one more this thing. So now you see another control net coming in. And then you do the same thing again, repeat this, put some U and V, and somewhere for these set of control points, 4 points. So this point is what? It will be a point on
The Bezier surface for the value that we
Bezier
chose.
surface for the value, let's say Ui, comma, Wj. All the guys are there or not? I think everybody is in different direction now. Okay, so this is basically extension of same de Castley algorithm. And then you have the on the surface. Very simple. You can use a successive linear interpolation on either side and then do this process for the Bezier surface. And you can do the same thing with the binomial expression or the on the Bernstein basis form also. Okay, so you can easily generate a Bezier surface either this way or the other way. Okay, which will involve double summation. I don't know whether I have that equation. So which will involve a double summation. If you remember your Bezier curve. So we use the Bij, N, I, right? So here what will happen is that this goes from I to this thing. So in this particular case, what will happen is that you have to have double summation sign. Okay, I goes from 0 to let's say N and J goes for M, something like that. And then you'll have Bij and then you have J J function, and then you will have J of U, and then let's say you will have M of U W or something. So this is an entire summation over M and N. Remember, N could be different on either side of the degree, could be different on either side of the parameter. That is why you have not necessarily N on both indices. It could be N on one and M on the other. And all the things are pretty much the same. There's absolutely no difference. Basis function behavior, your surface behavior is very similar to what you had in terms of curves on that. Is it okay? Little better?
Yes, sir.
Now reduced to only one guy. So how many guys are there now?
It's clear, sir.
It's
We are
clear?
there. We are
Ah.
just
Yes, sir, it's clear.
observing.
Okay, hopefully all of you are also observing. So you can see some pictures that I am showing this from the book, and you can see the black color on the control net, and you can see like a mesh kind of a figure for the surface. So this is a Bezier surface, and you can see these kinds of things are the control net that they are showing on both directions. Not very clear on the other direction, but something like this. But this is, so you can see that even if you move one point on that net, you can see that there is a change in the entire surface. Of course, it's very difficult to see here, but the idea is that if you change one point, it actually affects the entire surface. This we saw in the curve, right? If you change one control point on a Bezier curve, it propagates through the entire Bezier curve. And this is a problem for the surface also. But of course, it's a nice one to do all the designs, but still it has the limitation that the degree is affected by the number of control points on either side, and there is no local control of these things. So this is another example for a 4x4 control net. All the pictures are 4x4, I think. Some of them may be a little different. So do you guys observe anything? What is the control net size here? So what is the size of the control net here?
By 2, it looks like for 8.
Sir, 3 by 3, sir, 9.
3 by 5.
3 by 3.
3 by 5.
3 by 3. Huh?
Is it not
3
5
by
by
5.
3?
So that means what is wrong here? There's something that is wrongly mentioned. What is this?
The point B33.
B33. So it should be
3, 5.
Yeah, it should be 3, 5. So this is actually a 3/5 control net, which is I have indicated at the top. That
In the previous slide, the number of control points in this side was not equal to the other side. Why was that? So?
you don't have to be. Then you, that is why I said, right, you have to have, you can have different sides of control points. It is need not be 3/3 always, or need not be 4/4. Okay, this means that if you have a 3/5, this means that you have a degree 2 in the U direction, and the curve in the V direction or W direction is degree 5. So for example, this will be a quadratic one, and this one you can see it is of a degree 4.
No, sir. Actually, I am saying that this is 3. If it is this, I don't mean that if U is 3, then W has to be 3. If U is 3, then this side number of control points, if it is 3, then on the other end also the number of points should be 3, right? Like
Correct.
here also.
But it
But
cannot be B 3, 3, right? It cannot be
Yeah.
B 3, 3. So it should be B.
3,
So this is 0, 1, 2, right? So this is 0, 1, 2. So this is B. Remember, this is B0, 0. Let's say if it is B1, 0 and B2, 0. So you are going to increase. So this is B21, B22. Where is B22? Yeah, B22, B23, B24. See, this has to be index 1 less than these guys, right? So this has to be B24. Isn't it? So assuming this is the U direction and this is the other one is the W direction. Yes or no?
Yes.
Okay, so they have kind of mentioned it wrongly on that. But did you guys understand the degree can be different on U direction and on the W direction? But your entire curve surface, you can see that it behaves like a quadratically in this direction, and you can see that it is a degree 4 in the other side. And you can see you can create lots of different nice surfaces by this kind of differential degrees on either side. Okay, it just doesn't mean that you have to follow the same degrees on either side of the thing. Okay, that is one thing that you have to look at it.